Well, students, in this lecture, we will do some exercise problems from chapter number 3. Let us take up the problem number 8. The problem says that if an invertible matrix has a LU factorization, then we have to show that all its principal minors are non-zero. Let us see how to prove this result. Let us take A1, A2 up to AN as the principal submatrices of A. Then we have to show that determinant of AK is not equal to 0 for each K, right? You should note that this result is not true for any invertible matrices. It is true only for those invertible matrices for which LU factorization is possible. You should try to see some examples where the matrix is invertible, but still some of its principal minors are 0. You can easily get such examples. Now, given that A has LU factorization, it means what? There exists a lower triangular matrix L and a upper triangular matrix U such that A can be written as L into U, right? So that implies that determinant of A is going to be determinant of L into determinant of U, and determinant of A is not equal to 0 implies determinant of L is not equal to 0 and determinant of U is not equal to 0, right? Now L is the lower triangular matrix, so its determinant is the product of its diagonal element. Similarly, all its principal minors will also be equal to the product of the diagonal element of that submatrix, right? Therefore, we will have LK will also be the product of the diagonal elements of the principal minus, where LKs are the principal submatrix of L. And this is also true for the upper triangular matrices. Therefore, U will also satisfy the same property. And since determinant of L is not equal to 0, you can see that determinant of LKs are not equal to 0. And also determinant of UKs are not equal to 0. Now, since AK is equal to LK into UK, we see that determinant of AK is also not equal to 0 because it is the product of the determinant of LK and determinant of UK. And this is true for all K, and that completes the solution. Next, let us take the 18th problem. Show that the norm defined on the set of all n cross n matrices by norm A is equal to maximum over all the elements of A by taking their absolute values. And this is not a subordinate matrix norm to any vector norm on Rn. This is what we have to show. It may look a bit difficult, but it is actually a very easy problem. If it is a subordinate matrix to some vector norm, then it has to satisfy certain properties, right? We have listed 3 properties of subordinate norms. You can show that it doesn't satisfy one of those properties by taking some particular matrix and showing that that matrix, when applied to this norm, violates that property. Okay, for instance, you can take norm AB is less than or equal to norm A into norm B, right? So you can give some particular example of A and B and show that when you apply this norm to those matrices, the norm doesn't satisfy this property. I leave it to you to construct such examples. You can just stick with 2 by 2 matrices and do it. Next, let us take up the 19th problem. if A is an invertible matrix, show that its condition number kappa of A is greater than or equal to 1. This is a very important property of the condition number of a matrix, but it is very easy. If you recall, in condition number of a matrix, we always use the subordinate norm. This is what we have remarked when we were introducing the condition numbers. If the norm used in the condition number is a subordinate norm, then we know that norm of the identity matrix is equal to 1, right? That implies norm of A inverse is 1. That will immediately give you what you want, because you know that norm of A into A inverse is less than or equal to norm of A into norm of A inverse. Again, we are using this property of the subordinate norm, and that is precisely the definition of the condition number, right? Therefore, condition number is always greater than or equal to 1, whatever may be the invertible matrix A is. Next, let us take the problem number 21. The problem says that you have n cross n matrix, and K2 and K infinity of A are the condition number of the matrix computed using the subordinate matrix norm corresponding to Euclidean norm and the L infinity norm. So kappa 2 of A is therefore computed using the subordinate norm corresponding to the Euclidean norm. And similarly, kappa infinity of A is norm A infinity into norm A inverse infinity. Okay, so in the exam also I will probably give you directly kappa of infinity. It means I'm using the L infinity norm as the vector norm, that is the maximum norm, and the corresponding subordinate norm is denoted by this symbol. And similarly, we have one more, K1 of A, that is the condition number with respect to the subordinate norm, subordinate to L1 norm. Okay, so these notations are to be remembered when you are solving any problem. So here we are taking two different condition numbers of the matrix A. One is computed from the norm corresponding to Euclidean norm, that is L2 norm, and the other one is computed using the subordinate norm corresponding to L infinity norm. Now we have to answer the following. Determine all the diagonal matrices such that kappa infinity of A is equal to 1. Now, how will you find that? Well, you just write the matrix A is equal to A11, A22, and so on, ANN, and 0, 0, right? Why I'm taking this? Because we have to find all the diagonal matrices such that kappa of infinity is 1. So you just impose this condition, A infinity, A inverse infinity. You can see that this should be equal to 1. Now you know the formula for this, and similarly you know the formula for this. From here you can see what kind of AIIs will give you this. Okay, these are precisely A11 should be equal to A22. Everybody should be equal. Then you will get it, right? So once you write this and write the formula for these norms, you will immediately get this condition. I'll leave it to you to complete this. The next question is, you are given a matrix Q, which is an orthogonal matrix. Then show that kappa 2 is always equal to 1. That is, the condition number of a orthogonal matrix under Euclidean vector norm is always equal to 1. That is what we have to show. And this is not very difficult, because you can see that if the matrix is orthogonal, then you have Q transpose Q is equal to I, right? And that will tell us that all its eigenvalues are 1, right? For all I equal to 1, 2, up to n. And from here, you can see that norm Q2, that is nothing but the maximum of root of mod lambda i's, right, of Q transpose Q. And that is equal to 1. And similarly, you can also see that Q inverse, which is just Q transpose, that is also equal to 1. And that will immediately tell you kappa of Q with respect to 2 norm is actually equal to 1. Okay. The last question I will leave it to you to complete. Next, let us take up the 23rd problem. In this problem, we are interested in solving the system AX equal to B, where A is given by 1, 2, 1, 2.01. Our interest is to estimate the relative error in the solution X in terms of the relative error in B. That is what is asked here. If you slightly change the vector B, how that will affect our solution X. If you recall, we have done an estimate on relative error in X in terms of the relative error in B. We basically have to use this inequality, and also we have to check our result with a particular vector B given by 4, 4, and its approximation is given by 3, 5. In all our calculations, we are asked to use maximum norm at the vector level. Therefore, we should know what is the corresponding subordinate norm, so that wherever the matrix norm comes, you have to use that subordinate norm. As we know, if the maximum norm is used, then its corresponding subordinate norm is the maximum row sum norm. Okay, let us see what we have to do exactly in this problem. Of course, we have to use the estimate that we have established in our class, that is x minus x tilde divided by x. That's in a sense relative error in the solution vector. And we have seen that that is less than or equal to the condition number of the matrix A, kappa of A, which is nothing but norm A into norm A inverse into the relative error in the right hand side vector B, right? So this is what we have shown in the class. We have to use this inequality precisely in the present problem. Note that A is given by 1, 2, 2 and 2.01, and therefore we have to first find the norm of A and norm of A inverse. Remember, this inequality holds for any norm that we use. Okay, in particular, in this problem, we are asked to use maximum norm. That is what is L infinity norm, right? So we have to use everywhere L infinity norm in our calculation. In the condition number also, it should be kappa infinity. Now, if you ask what is the matrix norm subordinate to this L infinity norm, as I told, it is the maximum row sum norm, and that will happen to be 3.01 in the case of the matrix A, and in the case of matrix A inverse, it is, in my calculation, it is coming to be 401. That implies kappa infinity of A is the product of these two numbers, that happens to be 1207.01, right? Therefore, you have norm x minus x tilde divided by norm x. This is what we want to estimate in the L infinity norm, and that is less than or equal to 1207.01 into the other one. That is the relative error in the vector b tilde when compared to the vector b. Again, that has to also be done in the maximum norm. So this is what we want to get. That is, predict how slight change in b, that is, this is the slight change in b, will affect the solution x. So it affects at most in this way. Okay, this is the maximum number that your relative error in the solution can have. That is the answer finally. Now, in particular, we want to take b to be 4, 4 and b tilde to be 3, 5. It means you put b and b tilde on the right hand side and see whether the upper bound obtained here is really respected. Because once you put b and b tilde, you can exactly find this number, right? So the left hand side can be exactly found, and we want to check whether our prediction is correct. It means this number, whatever you get, is it really less than or equal to the number that you get here as upper bound when you put b and b tilde as these given numbers? Okay, let us check that. First and foremost, you have to find b norm, which is actually 4, and b minus b tilde, that is going to be in the L infinity norm, it is 1, right? Therefore, right hand side is going to be, that is the upper bound is going to be 1207.01 into 1 by 4, right? That is going to be something approximately equal to, maybe less than or equal to 301.753 in my calculation. Please check this. Okay, so therefore we are supposed to get x minus x tilde divided by x. Up to now, we do not know what is this number because we have not calculated x and x tilde. But what we know is this is going to be surely less than or equal to 301.753. That is our analysis says. Okay. Let us cross check our analysis. How? Well, you know b, you know a, therefore you can find what is x by directly solving it. X is given by 4, 0, and similarly x tilde is given by minus 397 to 100. Okay, therefore norm x minus x tilde in the infinite norm divided by norm x, again infinite norm, is equal to 401 divided by 4, and that is equal to approximately 100.25, maybe exactly, and that is obviously less than 301, which is our predicted number. So our analysis is actually correct. Okay, so this is finally what we have to check as per this problem. You first predicted how this number will be. It means you estimate. Okay, so here by predicting we mean estimate. It means find an upper bound for this number. We found it, and go and check it with the explicit calculation that we have checked here, and therefore our problem is solved. Let us do few iteration problems. Let us take up this 30th problem. Write the formula for Jacobi iteration sequence of the system given like this. That is not a difficult one because we know how to write it. You just have to keep the diagonal elements on the left hand side, push everybody on the right hand side, and then divide both sides by the diagonal entry. In that way, we will get x1 of k plus 1 is equal to 1 by 7 into 2 plus 15x2 k plus 21 x3 k, right? And similarly, the other terms we can write. Now, the second part is interesting. Without performing the iteration, show that the sequence does not converge to the exact solution of this system. Even if you perform the iteration, you cannot conclude by numerically observing that your sequence is going away from your exact solution, right? It may happen that your sequence may go away from the solution for some iterations, and then it start turning back and coming and converging to the solution. Anything can happen. Therefore, just by numerically observing few terms, however large number of terms that you compute, you really cannot conclude on whether the sequence is converging or not. But still, to be on a safer side, we tell that don't perform the iteration, because some students will perform some 10 iterations, and from there they conclude, look, solution is this, whereas the sequence is going away from the solution, therefore it diverges. You cannot conclude like that. Okay, even you calculate 100 terms and see that your 100th iteration is far away from the solution, doesn't mean really that your sequence is diverged. Okay, it means then turn back and then may go and converge. So anything can happen. So you need to confirm whether the iteration is converging or not converging through certain theoretical arguments only. Numerically, one can have some feeling that yes, it may converge or it may not converge, but you cannot conclude anything. Now, how to do this problem? Well, in the last lecture, we have also given one necessary and sufficient condition for convergence, right? So that condition can be used to check if it is going to converge or not. If you recall, the condition is that if the spectral radius of the iteration matrix is less than 1, then the sequence will converge. And converse is also true. Therefore, one can check the spectral radius of the iteration matrix. For that, we first need to get the iteration matrix. You can see by writing these two equations explicitly, the iteration matrix B is given by 0, 15 by 7, 3, 7, 0, minus 5, minus 7, minus 5, and 0. Recall what is this iteration matrix? Iteration matrix is nothing but when you write these three components in the matrix form, that will give you the Jacobi matrix. Xk plus 1 is equal to B xk plus C, right? Similarly, you can also write the Gauss-Seidel method in this form. How? You will have some k plus 1 terms on the right hand side, right? You push them to the left hand side and take the inverse on both sides. In that way, even Gauss-Seidel method can be put in this form. Please write it explicitly and see that. Okay, coming back to this problem, you have B like this. That's the Jacobi matrix or the iteration matrix for this particular system when Jacobi method is used. Now we have to find the spectral radius of B, which is actually defined by maximum over I is equal to 1 to n. Here it is 3 mod lambda I, where lambda i's are eigenvalues of the matrix B, right? So you have to compute the eigenvalues of this matrix. You can see that the eigenvalues of this matrix B are given by lambda 1 is equal to 2, lambda 2 equal to 3, and lambda 3 equal to minus 5. Therefore, the spectral radius of the matrix B is 5, which is obviously greater than 1. That implies that the Jacobi sequence doesn't converge. And one more question is also asked in this problem. Can you make a suitable change of rows so that the resulting system is diagonally dominant? You can see that as such, the coefficient matrix is not diagonally dominant. You can see the first line itself says that. Now, can you make some row interchange and make this system finally a diagonally dominant system? Well, by a direct observation, we can see that this system cannot be written as a diagonally dominant system by making any row interchanges. Therefore, the answer is it is not possible.